Good morning, Townview. So today we're going to be talking about thermodynamics. So grab your journals, top of your page, you're going to write thermodynamics. So thermo means heat, and then dynamics means change. So heat change. Let's go ahead and move on. All right, so energy is exchanged in both physical and chemical changes. There are two types of energy transfer. There are physical changes and chemical changes. So a physical change, an example of that is going to be like, what's an example of a physical change? Like melting ice. So if you melt ice, you have to add energy to the ice to convert it to water. So that's an energy transfer. Heat is being absorbed from the environment into the ice. An example of a chemical change is like burning paper. So if you burn a sheet of paper, you're releasing energy. So there's energy in those chemical bonds, and when you burn the paper, you're releasing that energy. So these are the four types of energy that we're going to be talking about this semester, for the rest of this semester. The first one is going to be potential. Most of y'all are familiar with potential from junior high. So potential energy, that's stored energy, and it depends on the location, like a car on a hill. So here's our little hill. So I don't want to draw a car. I'm just going to draw a circle. This is going to be our car. So a car at the bottom of the hill doesn't have that much energy. But a car at the top of the hill has a lot of stored energy. All it needs is a little bit of push to release that energy. The next type of energy, which you're also familiar with, is going to be kinetic energy. This is the energy of motion. So this boulder, as soon as we push it over the hill, once it reaches this point right here, it's got a bunch of motion, and that motion is going to be kinetic energy. It's a really bad arrow. The next type of energy is going to be chemical energy. So chemical energy is a form of potential energy. So it falls under the potential category. And it's related to the structural arrangement of atoms or molecules. So an example is going to be something like propane. So propane is C3H8. And when you burn propane, you're releasing the energy from those chemical bonds. But different chemicals have different potential energies. Our last type of energy is going to be thermal. Thermal is a form of kinetic energy, and it results from the motion of particles and is transferred as heat. So an example of thermal energy is, think about a candle. Here's a little candle. Here's our wick, and then we're going to light up our wick. So it looks like that. Has anyone ever put their hand above a candle? I'm sure everyone's tried it once. So when you do that, what you're feeling is the air that's around the flame. As it heats up, what does it do? Does it go up or does it go down? So the air that surrounds the flame, it goes up. And what you're feeling is that air that's rising. So this is the type of kinetic energy. That's thermal energy, and this is your hand. All right, let's go ahead and move on. So our next slide is going to be the law of conservation of energy. You don't need to write all of this. What you do need to write, though, is that energy cannot be created or destroyed. This is the important thing to know about the law of conservation of energy. If you want the long version is that that the total amount of energy in a closed system remains constant. Now, what's a closed system? A closed system is anywhere you're conducting your experiment. So let's say you have a beaker If you're using a beaker for a chemical reaction, the chemical reaction is going to be your system, and then everything surrounding everything that surrounds it is going to be your environment. The environment's also referred to as the universe. So everything outside of the system is the universe. So there's this really cool physics experiment, not experiment, but a demonstration that physics professors do, where a professor will stand right here. This will be your professor. And they'll take this ball and they'll put it right up to their nose. And this ball will be really heavy. It'll be like a 10 or 20 pound ball. And they put it right up to their nose, and then they release it. And then what it does is it swings over to this side, and then it swings back. When it swings back, is it possible for it to touch their face? No, because it would require additional energy for it to actually touch their face. But it looks so scary coming back like straight towards you. I have the thing that's needed to set that demo up, but I'm afraid of breaking my teeth. But yeah, it's a very cool pendulum test, and it shows you how brave your physics professor is. All right, so more about the conservation of energy. So energy is measured in joules. That's just one thing to know. This was like 3 slides. I condensed them to 1 slide. But all you need to know about energy is that the unit for it is going to be joules. Joules are just a J. Now take a look at the quick question that we have underneath. So if a system started with 1,000 joules of electrical energy and the energy was converted to light, how much light energy would there be? How much light energy would there be? So if 1,000 joules of electrical energy is converted to light, how much light energy should there be, theoretically? It's going to be 1,000 joules. So this is theoretical. It's never 1,000 joules. You always lose some energy to the wires, because the wires, they also heat up, and heat takes away from that energy. But theoretically, you should get 1,000 joules, but you never will. Just a heads up. It's an efficiency problem. Anybody know how much efficiency you get out of your car's engine? Like, how much energy are you actually taking from the fuel? Anybody want to guess? It's roughly 30%. So if you take that fuel and you burn it in a factory, you get about 60% out of that fuel. But in your car, you only get about 30%, which is why cars are said to be very inefficient. And that's why they say electric cars are better, because if you burn the same fuel in a factory, you should get twice the miles in an electric car. So let's go ahead and move on. So conservation of energy, this is more likely the type of problem you're going to see. So I'm going to give you guys 3 minutes to solve both of these. So just give it your best shot. I know y'all can do this. All right, so let's take a look at the first one. We have 25,000 joules of kinetic energy. So 25,000. And then 18,000 is converted to mechanical energy. So that's 18,000 over here. Plus 6,000 is going to be heat energy. And then the last of it's converted to heat. So plus X. We're just solving for X here. So 18 plus 6 is going to be what? 24,000. And then we just need to isolate our variable. So to do that, we're going to subtract 24,000 from both sides, which leaves us with what? It leaves us with 1,000. So X equals 1,000. Who got 1,000? So this is a simple type of question. This is what I think they're going to ask you with regard to conservation of energy. So let's go ahead and look at the next one. The next one is the same thing, except now they're using percentages. So 20,000 joules of thermal energy is released through burning of methane. 1/4 of that energy is converted to light, while the rest is converted to heat. So who's seen those light bulbs that let out a bunch of heat? Who has those types of bulbs in your bathroom? Y'all know what I'm talking about? You turn on the light and it gets hot. So those are the old types of lights, and those types of lights convert a lot of electricity to heat, which is why they're very inefficient. So back in my day, and I'm talking like the 2000s. In the 2000s, most of the light bulbs that we would have around the house are going to be either 60 watt or 100 watt. 100 watts of energy is a lot of power. I ran a 100 watt light bulb in my closet, and it set a fire once. I left the light on for very long. It wasn't like a big fire; it was a very tiny fire. I was able to stop it on my own. But basically, I left the light on for a couple of days, and like I came back and I opened the closet, and I had this like Tasmanian devil toy. It was a plush, and then it was like completely melted. So it didn't start a fire, but it was so close. My brother, he's the one who started fires. He burned down two of our houses. My little brother's the worst. I'm just kidding. He's all right. Y'all want to know how he did it? So he would. So it's my mom's fault. We had curtains in the house. He would get a candle, and then he would like take matches and then play with matches and then throw them into the candle. And then he would take tissues, rip them up, and throw them into the candle. And I'm talking about a 4-year-old brother. And one time, like the curtain, it got caught in the candle, and then that was it. That house burned down. But he did that twice. He burned down a really nice house that we lived in, and then he burned down a really not so great house. This is gonna get cut out of the video, by the way. But yeah, my brothers burned down 2 of our houses. I remember the fireman came to the house, and they were trying to figure out how did this fire happen, and he went to my little brother. He was like, "You were doing this," and then my brother was just like crying, like, "No, I didn't do it," but he did it. Anyway, back to inefficient light bulbs. So 20,000 joules of energy from burning methane. 1/4 of that is converted to light. The rest of that's converted to heat. So a quarter of 20,000 is going to be 5,000. So 5,000 joules of light, and then 15,000 joules of heat. So this type of question, we could talk about how to solve it, but y'all know how to work with percentages. You just multiply by the percentage. So 1/4, that's going to be 0.25. You just multiply that by 20,000, and then that's going to give you your the 5,000 that we have here. And then 3/4 or the rest is going to be the heat. All right, so let's move on. So now we're going to talk about heat. But before we do, I do want to ask you guys a question, because this is a question they ask every single year. So we have 2 metal cubes, and we can say that they're aluminum. We have 2 metal cubes. This one is 20 degrees C. This one is 20 degrees C. And then this one is 100 degrees C. So they're separated, and then we bring them close together until they have full contact. So now they're touching. What's going to happen? Is the cold going to transfer from the cold one to the hot one, or is the heat going to transfer from the hot one to the cold one? Who thinks that the heat is going to move? Hands up. Who thinks that the cold is going to move? Hands up. All right, so this is just a super basic question, but they ask it every single year. What you need to know about heat transfer is heat is a real thing that can be measured. Cold is just the absence of heat. So if you don't have heat, you have cold. So you can't move heat. You can't move cold, I mean. What you can move is heat. So heat is transferable. So this is what you need to know. Energy flows from hot to cold. Energy flows from hot to cold. Make sure you write that down. The warmer substance gives energy to the cooler one. And just a tip for you guys, when you put stuff in the fridge, don't ever put something hot in the fridge. It'll ruin all the food in your fridge. Has anyone ever done that? Put something really hot in the fridge? All right, you shouldn't. You gotta wait for it to get cool and then put it in the fridge. Yeah, it'll ruin the food. Because if it's really hot, it's got a lot of heat in it, and then that heat is gonna dissipate into all the food that's in the fridge. It's gonna ruin the food in the fridge. All right, so another thing to know is here we talked about temperature, but another thing you need to know is that this is also energy. So we can call this 100 joules, and then we can call this 20 joules. Now, after they've equalized, so down here they're going to equalize, and we can say that they equalize around 60 degrees Celsius. When they do that, their energy also transfers. So energy is transferring from the hot one to the cold one, and now they should both have around 60 joules of energy. So just another thing to know is when heat is transferred, there is a change in energy. So energy and heat, they're basically the same thing. So heat is energy. So when heat is transferred, there is a change in energy. So heat can be transferred in three ways. So the first type is going to be conduction. The next type is going to be convection, and the third is radiation. I want you to leave space between these because we're going to write some stuff about them. So just the three methods of heat transfer are conduction, convection, and radiation. And the next 3 slides will elaborate. All right, let's move on. So the first type of heat transfer is going to be conduction. And conduction is going to be the direct transfer of heat through contact. So who here has one of those stovetops that has one of these coils? Who here has a coil stovetop? Hands up if you got a coil stovetop. All right, so if you have a coil stovetop, that's conduction. That's going to be transfer via contact. The important thing to know here is there's contact. So one side gives you a positive charge, the other side gives you a negative charge, and as the electrons flow through the wire, they heat up, and that's conduction right there. Does anybody have one of those flat top stoves? All right, so there's 2 types of flat top stoves. There's the type that gets red when you turn it on, and then there's the type that doesn't get red. Who has the type that gets red? Okay. And then who has the type that does not get red? Okay. So that's called an induction stovetop, the one that does not get red. So does your stovetop, like if you remove the pan, can you touch it or is it hot? Okay. So what I've heard about induction stovetops is they don't get hot or they do get warm, but they don't get as hot as the red one. So the red one is, it is using conduction. But there's a new type of stove. Do y'all want to see it? Are y'all interested? No, y'all not. So the important thing to remember here, this is direct transfer through contact. All right, let's move on. So our next one is convection. You've all heard of a convection oven. So I'll show y'all a picture of a convection oven. We'll talk about it. But before we do, just know that convection is going to be the transfer of heat by motion of fluids. We talked about this last semester, but gases and liquids are both considered fluids. So the air inside of your oven, that's the fluid that's moving around. All right, let's move on. So the last type is going to be radiation. And radiation is heat that is transferred through electromagnetic waves. One important thing to know about radiation, and this they test on every single year. So radiation is the only form of heat transfer that does not require matter. It does not require matter, which means radiation can travel through space. So here's the sun. Here's our planet. We get all of our energy from the sun. And if we needed a medium for that energy to transfer, it wouldn't be able to get here. Thankfully, radiation can travel through the vacuum of space, and that's the way the energy actually reaches us. So radiation does not require matter to transfer. So conduction requires solid matter. Convection requires fluid matter. And radiation requires no matter. Another example of radiation is going to be your microwave. So when you heat something in the microwave, you're using radiation to heat it up. That radiation causes the particles to move faster, which causes the food to get warmer. All right, let's move to the next slide. So this image I like a lot because it shows you all three in one image. So here we got some logs burning. And most people, when they're around a campfire, they'll do what this guy is doing. They'll put their hands above the fire because that's where you get the most heat. So here you're getting the convection. So as the air gets hot down here in this area, that air travels up and then that warms your hands. That's going to be convection. This one right here is doing conduction. This should be in the flame. It should be a little bit lower and actually touching the flame. But you can see that the conduction is occurring throughout the entire bar. So the heat is traveling upwards to this person's hand. And then this last person, this is the person who doesn't want to smell like smoke. They're really far away from the fire. And all they're getting is the glow from the fire. This person is very cold. You don't get very much heat from the radiation. We know that it exists. We see it. That's the light that's glowing on that person. But they don't get quite as much heat as the convection or conduction guy. All right, so let's go ahead and do some practice. So for each illustration and explanation, decide what is the medium the heat is being transferred through and what method of heat transfer is being depicted. So here's our images. I'm going to label these 1, 2, 3, 4, 5, and 6. And I'm going to see if I can make the text a little bit larger. But if I can't, y'all should still be able to do these. All right, so don't worry about proof. All you're doing is medium and heat transfer method. All right, so specific heat. Does everything heat up and cool down at the same rate? What do y'all think? All right, good. So different substances have different capacities for storing energy. It can take 20 minutes to heat water to 75 degrees C. The same mass of any metal could only require 5 minutes. So different mediums require different amounts of heat to change their temperature. The reason for that is because of specific heat. So specific heat, I want y'all to write the definition for it. Specific heat is the amount of heat needed to raise the temperature of 1 gram of any substance by 1 degree Celsius. So the amount of heat needed to raise the temperature of 1 gram of any substance by 1 degree Celsius. So the higher this number, the more energy is required to heat that thing up. The lower this number, the more quickly that thing gets really hot. So the thing with the lowest number on this list is going to be gold, 0.13. That means gold will get really hot really quick. That's why gold is such an excellent conductor. That's why your HDMI cables, your really good HDMI cables, are gold plated. So silver is also pretty good. Not as good as gold, but it's pretty good. But here's water. Water is the thing we're going to be working with the most. Water has a specific heat of 4.18. We talked about how the specific heat of water being high is very important to the planet because the ocean absorbs so much of the heat in the environment and it keeps the planet cool. So living close to a lake, it doesn't get as hot because the lake, it absorbs a lot of the heat that the sun gives off. Air is, water requires 4 times as much energy as air to heat it up. So air gets hot pretty quick. Let's move on. So next we got a couple definitions. So conductors, we know what conductors are. Conductors are materials that transfer heat easily and quickly. You can write this if you know it. There's no need to write it. Remember, metals are the best conductors. And the reason they're good conductors is because they have low specific heat. That means they absorb heat very easily. So the opposite of a conductor is going to be an insulator. Insulators do not conduct heat easily. They have a high specific heat. Examples of insulators are going to be things like water, glass, plastic, rubber, and air. Water is not an insulator when we're talking about electricity because you've seen electricity conduct water. Or sorry, water conduct electricity. But water will insulate heat. That's why engines run water to keep the engine cool. Materials that trap air, such as foam, fur, and feathers, are the best insulators. Who here has ever used a Yeti, like one of those Yeti coolers? All right, you've seen those coolers. You put something in those, and it stays cool all day. That's because of the design and all that air that's trapped on the inside. That air is a very good insulator, and it'll absorb a lot of that heat. Keep it from entering your box. All right, let's move on. All right, so don't worry about this. Here's our formula. So let's all write our equation, and then I want us to define the equation. So Q is going to be the heat energy. This is where our joules go. M is going to be the mass of our substance. Make sure that it's a lowercase m because capital M means something completely different. So lowercase m for mass. And then most likely this is going to be plugged in as grams. So Cp is going to be our specific heat. Our specific heat has a weird unit. It's going to be joules over grams times Celsius. Joules over grams times Celsius. And then delta T. Anybody remember what delta T is? It's the change in temperature. And the change in temperature is going to be put in Celsius. So you don't need to convert to Kelvin here. All right, so this formula is very often referred to as MCAT. And the way to remember is anytime you're talking about heat, you're going to use the formula Q is equals to MC delta T. So MCAT. Now let's go ahead and practice with it. Here's our first problem. How much temperature can be expected? How much temperature change can be expected when 250 grams of water absorbs 50 joules of heat? So let's go ahead and write out our formula. So Q is equal to MC delta T. So we're solving for temperature change. They give us our joules. So that's going to be our Q. And that's going to be 50/50 is equal to 250 grams. And we're talking about water here. So we need the specific heat of water, which is 4.18. And then we're solving for delta T. I'm just going to plug in an X. So how do we solve this? What's our first step? Multiply what? 250 times 4.18. And that gives us 1,045. And then these go away. And now X times 1,045. What's our next step? All right, so we're going to isolate our variable. So 1045. This goes away. And 50/50 divided by 1045 will give us 4.83. So our temperature change is 4.83. And then that's going to be in Celsius. Was that easy? All right, so let's try the next one on our own. All right, so 15.75 grams of iron. I'm going to start by writing my formula. So Q is equal to MCAT, MC delta T. So Q is given to us. It's right here. So 1086.75 is equal to 15.75. And our temperature changes from 25 to 150. We're solving for C here. I'm just going to put an X. And our temperature change is 150. So what's our first step here? What's our first step? So 15.75 times 150. Uh, 2,362. Is that what y'all got? 2,362. Did somebody get? That's what y'all got, right? All right. So X goes here, and then what's our last step? We're gonna divide both sides by 2362. This goes away. So 1086.75 divided by 2,362.5. And then X is going to be equal to 0.46. And let's see if that's correct. So over here, it gives us iron, which is 0.45, which is close enough. So our X is, our CP is equal to 0.46. Who else got 0.46? All right, good job. Last one, and then y'all can turn in your notes.